The genotype of a goat that is heterozygous for restricted ears might be written L, EIR, or simply plus higher. If genotypes of more than one locus are presented together, a space may separate them. A goat heterozygous for a pair of alleles that produce restricted ears and heterozygous for another pair of alleles that produce goiter can be designated by L, EIR, G per gram. Ratios in simple crosses. Now that we have had some experience with genetic crosses, let's review the ratios that appear in the progeny of simple crosses, in which a single locus is under consideration. Understanding these ratios and the parental genotypes that produce them will allow you to work simple genetic crosses quickly without resorting to the Punnett square. Later, we will use these ratios to work more complicated crosses entailing several loci. There are only 4 phenotypic ratios to understand table 2. The 3:1 ratio arises in a simple genetic cross when both of the parents are heterozygous for a dominant trait A_A. The second phenotypic ratio is the 1:1 ratio, which arises in the progeny of crosses between two parents heterozygous for a character that exhibits incomplete dominance AXA. The third phenotypic ratio is the 1:1 ratio, which results from the mating of a homozygous parent and a heterozygous parent. If the character exhibits. Institute for Advanced Studies, Job 7. Ratio genotypes of parents genotypes of progeny type of dominance 3. 1 A dominance. 1, 2, 1 XAB, AAGIY incomplete dominance. 1, 1 SA dominance or incomplete dominance. Ag XA OAG, voting for incomplete dominance, uniform potency at XA Allah dominance or incomplete dominance XA Allah dominance or incomplete dominance % Allah dominance or incomplete dominance LX ag underscore dominance. Mote, a line in a genotype, such as 4 indicates that any allele is possible. Dominance, the homozygous parent in this cross must carry 2 recessive alleles AXA to obtain a 1:1 ratio because a cross between a homozygous dominant parent and a heterozygous parent AXA produces only offspring displaying the dominant trait. For a character with incomplete dominance, a 1:1 ratio results from a cross between the heterozygote and either homozygote AXA or AXA. The fourth phenotypic ratio is not really a ratio, all the offspring have the same phenotype. Several combinations of parents can produce this outcome. Table 2. A cross between any two homozygous parents, either between two of the same homozygotes AXA and AXA, or between two different homozygotes AXA produces progeny all having the same phenotype. Progeny of a single phenotype can also result from a cross between a homozygous dominant parent and a heterozygote AXA. If we are interested in the ratios of genotypes instead of phenotypes, there are only 3 outcomes to remember. Table 3, the 1:1 ratio produced by a cross between two heterozygotes, the 1:1 ratio produced by a cross between a heterozygote and a homozygote, and the uniform progeny produced by a cross between two homozygotes. Table 3. Ratio genotypes appearance of progeny. We will now extend Mendel's principle. These simple phenotypic and genotypic ratios and the parental genotypes that produce them provide the key to understanding crosses for a single locus and, as you will see in the next section, for multiple loci crosses. We will now extend Mendel's principle of segregation to more complex crosses for alleles at multiple loci. Understanding the nature of these crosses will require an additional principle, the principle of independent assortment. Dihybrid crosses. In addition to his work on monohybrid crosses, Mendel also crossed varieties of peas that differed in 2 characteristics. Dihybrid crosses. For example, he had one homozygous variety of pea that produced round seeds and yellow endosperm. Another homozygous variety produced wrinkled seeds and green endosperm. When he crossed the two, all the F1 progeny had round seeds and yellow endosperm. He then self-fertilized the F1 and obtained the following progeny in the F2: 315 round, yellow seeds, 101 wrinkled. Yellow seeds, 108 round, green seeds, and 32 wrinkled. Green seeds. Mendel recognized that these traits appeared approximately in a 9:3:1 ratio, that is, 9/16 of the progeny were round and yellow, 3/16 were wrinkled and yellow, 3/16 were round and green, and 1/16 were wrinkled and green. The principle of independent assortment. Mendel carried out a number of dihybrid crosses for pairs of characteristics and always obtained a 9:3:1 ratio in the F2. This ratio makes perfect sense in regard to segregation and dominance if we add a third principle, which Mendel recognized in his dihybrid crosses, the principle of independent assortment, Mendel's second law. This principle states that alleles at different loci separate independently of one another. A common mistake is to think that the principle of segregation and the principle of independent assortment refer to two different processes. The principle of independent assortment is really an extension of the principle of segregation. The principle of segregation states that the two alleles of a locus separate when gametes are formed. The principle of independent assortment states that when these two alleles separate, their separation is independent of the separation of alleles at other loci. A. Pea generation. Round, yellow wrinkled, green. Seeds. Let's see how the principle of independent assortment explains the results that Mendel obtained in his dihybrid cross. Each plant possesses two alleles coding for each characteristic, so the parental plants must have had genotypes RRYY and RRYY. Figure 11a. The principle of segregation indicates that the alleles for each locus separate, and one allele for each locus passes to each gamete. The gametes produced by the round, yellow parent therefore contain alleles Y, whereas the gametes produced by the wrinkled, green parent contain alleles Y. These two types of gametes unite to produce the F1, all with genotype RRYY. Because round is dominant over wrinkled and yellow is dominant over green, the phenotype of the F1 will be round and yellow. When Mendel self-fertilized the F1 plants to produce the F2, the alleles for each locus separated, with one allele going into each gamete. This is where the principle of independent assortment becomes important. Each pair of alleles can separate in two ways. One R separates with Y and R separates with Y to produce gametes Y and Y, or two R separates with Y and R separates with Y to produce gametes Y and Y. The principle of independent assortment tells us that the alleles at each locus separate independently. Thus, both kinds of separation occur equally in all 4 types of gametes RY, and Y are produced in equal proportions. Figure 11b. When these 4 types of gametes are combined to produce the F2 generation, the progeny consists of 9/16 round and yellow, 3/16 wrinkled and yellow, 3/16 round and green, and 1/16 wrinkled and green, resulting in a 9:3:1 phenotypic ratio. Figure 11c. The relation of the principle of independent assortment to meiosis. An important qualification of the principle of independent assortment is that it applies to characters encoded by loci located on different chromosomes because, like the principle of segregation, it is based wholly on the behavior of chromosomes during meiosis. Each pair of homologous chromosomes separates independently of all other pairs in anaphase of meiosis, so genes located on different pairs of homologs will assort independently. Genes that happen to be located on the same chromosome will travel together during anaphase of meiosis and will arrive at the same destination within the same gamete unless crossing over takes place. Genes located on the same chromosome therefore do not assort independently unless they are located sufficiently far apart that crossing over takes place every meiotic division. The dihybrid test cross. Let's practice using the branch diagram by determining the types and proportions of phenotypes in a dihybrid test cross between the round and yellow F1 plants RRYY that Mendel obtained in his dihybrid cross and the wrinkled and green plants RRYY. Figure 13. Break the cross down into a series of single locus crosses. The cross RRXRR yields %2 round RR progeny and %wrinkled RR progeny. The cross YYXYY yields %yellow YY progeny and %green YY progeny. Using the multiplication rule, we find the proportion of round and yellow progeny to be %. The probability of round X%, the probability of yellow equals %4. 4 combinations of traits with the following proportions appear in the offspring: %RRYY, round yellow, %RRYY, round green, RRYY, %wrinkled yellow, and %RRYY, wrinkled green. Trihybrid crosses. The branch diagram can also be applied to crosses including 3 characters called trihybrid crosses. In one trihybrid cross, Mendel crossed a pure breeding variety that possessed round seeds, yellow endosperm, and gray seed coats with another pure breeding variety that possessed wrinkled seeds, green endosperm, and white seed coats. Figure 14. The branch diagram shows that the expected phenotypic ratio in the F2 is 279993331, and the numbers that Mendel obtained from this cross closely fit these expected ones. In monohybrid crosses, we have seen that 3 genotypes RR, and RR are produced in the F2. In dihybrid crosses, 9 genotypes, 3 genotypes for the first locus X, 3 genotypes for the second locus equals 9 are produced in the F2, RRYY. RRYY, 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 and RRYY. Institute for Advanced Studies, Jodhpur. Genotypes produced in the F2 of a cross between individuals heterozygous for N loci will be 3 if there is incomplete dominance. The number of phenotypes also will be 3 because, with incomplete dominance, each genotype produces a different phenotype. If the traits exhibit dominance, the number of phenotypes will be 2n, observed in expected ratios. When two individuals of known genotype are crossed, we expect certain ratios of genotypes and phenotypes in the progeny. These expected ratios are based on the Mendelian principles of segregation, independent assortment, and dominance. The ratios of genotypes and phenotypes actually observed among the progeny, however, may deviate from these expectations. For example, in German cockroaches, brown body color Y is dominant over yellow body color Y. If we cross a brown, heterozygous cockroach YY with a yellow cockroach YY, we expect a 1 ratio of brown YY and yellow YY progeny. Among 40 progeny, we would therefore expect to see 20 brown and 20 yellow offspring. However, the observed numbers might deviate from these expected values. We might in fact see 22 brown and 18 yellow progeny. Chance plays a critical role in genetic crosses, just as it does in flipping a coin. When you flip a coin, you expect a 1 ratio, percent heads and percent tails. If you flip a coin 1,000 times, the proportion of heads and tails obtained would probably be very close to that expected 1 ratio. However, if you flip the coin 10 times, the ratio of heads to tails might be quite different from 1. You could easily get 6 heads and 4 tails, or 3 and 7 tails, just by chance. It is possible that you might even get 10 heads and 0 tails. The same thing happens in genetic crosses. We may expect 20 brown and 20 yellow cockroaches, but 22 brown and 18 yellow progeny could arise as a result of chance. 72 L4 RRYYCCDY. Rewise. Expected proportions. Expected proportions. If you expected a 1 ratio of brown and yellow cockroaches, but the cross produced 22 brown and 18 yellow, you probably wouldn't be too surprised even though it wasn't a perfect 1 ratio. In this case, it seems reasonable to assume that chance produced the deviation between the expected and the observed results. But if you observe 25 brown and 15 yellow, would the ratio still be 1? Something other than chance might have caused the deviation. Perhaps the inheritance of this character is more complicated than was assumed, or perhaps some of the yellow progeny died before they were counted. Clearly, we need some means of evaluating how likely it is that chance is responsible for the deviation between the observed and the expected numbers. To evaluate the role of chance in producing deviations between observed and expected values, a statistical test called the goodness of fit chi-square test is used. This test provides information about how well observed values fit expected values. Before we learn how to calculate the chi-square, it is important to understand what this test does and does not indicate about a genetic cross. The chi-square test cannot tell us whether a genetic cross has been correctly carried out, whether the results are correct, or whether we have chosen the correct genetic explanation for the results. What it does indicate is the probability that the difference between the observed and the expected values is due to chance. In other words, it indicates the likelihood that chance alone could produce a deviation between the expected and the observed values. If we expected 20 brown and 20 yellow progeny from a genetic cross, the chi-square test gives the probability that we might observe 25 brown and 15 yellow progeny simply owing to chance deviations from the expected 20-20 ratio. When the probability calculated from the chi-square test is high, we assume that chance alone produced the difference. When the probability is low, we assume that some factor other than chance, some significant factor, produced the deviation. To use the goodness of fit chi-square test, we first determine the expected results. The chi-square test must always be applied to numbers of progeny, not to proportions or percentages. Let's consider locus for coat color in domestic cats, for which black color B is dominant over gray B. If we cross two heterozygous black cats B flat X B flat, we would expect a 3:1 ratio of black and gray K kittens. Most scientists use a 0.05 probability level as their cutoff value. If the probability of chance being responsible for the deviation is greater than or equal to 0.05, they accept that chance may be responsible for the deviation between the observed and the expected values. When the probability is less than 0.05, scientists assume that chance is not responsible and a significant difference exists. The expression significant difference means that some factor other than chance is responsible for the observed values being different from the expected values. In regard to the kittens, perhaps one of the genotypes experienced increased mortality before the progeny were counted, or perhaps other genetic factors skew the observed ratios. In choosing 0.05 as a cutoff value, scientists have agreed to assume that chance is responsible for the deviations between observed and expected values unless there is strong evidence to the contrary. It is important to bear in mind that even if we obtain a probability of, say, 0.01, there is still a 1% probability that the deviation between the observed and expected numbers is due to nothing more than chance. Calculation of the chi-square value is illustrated in figure 15. Penetrance and expressivity. In the genetic process considered thus far, we have assumed that every individual with a particular genotype expresses the expected phenotype. We assume, for example, that the genotype RR always produces round seeds and that the genotype RR always produces wrinkled seeds. For some characters, such an assumption is incorrect. The genotype does not always produce the expected phenotype, a phenomenon termed incomplete penetrance. Incomplete penetrance is seen in human polydactyly, the condition of having extra fingers and toes. There are several different forms of human polydactyly, but the trait is usually caused by a dominant allele. Occasionally, people possess the allele for polydactyly, as evidenced by the fact that their children inherit the polydactyly but nevertheless have a normal number of fingers and toes. In these cases, the gene for polydactyly is not fully penetrant. Penetrance is defined as the percentage of individuals having a particular genotype that express the expected phenotype. For example, if we examine 42 people having an allele for polydactyly and found that only 38 of them were polydactylous, the penetrance would be 38 40 seconds equals 0.9090%. A related concept is that of expressivity, the degree to which a character is expressed. In addition to incomplete penetrance, polydactyly exhibits variable expressivity. Some polydactylous persons possess extra fingers and toes that are fully functional, whereas others possess only a small tag of extra skin. Incomplete penetrance and variable expressivity are due to the effects of other genes and to environmental factors that can alter or completely suppress the effect of a particular gene. A gene might encode an enzyme that produces a particular phenotype only within a limited temperature range. At higher or lower temperatures, the enzyme would not function and the phenotype would not be expressed. The allele encoding such an enzyme is therefore penetrant only within a particular temperature range. Many characters exhibit incomplete penetrance and variable expressivity, emphasizing the fact that the mere presence of a gene does not guarantee its expression. BNC extensions of Mendelian principles, codominance, incomplete dominance, gene interactions, pleiotropy, genomic imprinting, penetrance and expressivity, phenocopy, linkage and crossing over, sex linkage, sex limited and sex influenced characters. Concept of gene, allele, multiple alleles, pseudoallele, complementation tests. Dominance revisited. One of Mendel's important contributions to the study of heredity is the concept of dominance, the idea that an individual possesses two different alleles for a characteristic, but the trait enclosed by only one of the alleles is observed in the phenotype. With dominance, the heterozygote possesses the same phenotype as one of the homozygotes. When biologists began to apply Mendel's principles to organisms other than peas, it quickly became apparent that many characteristics do not exhibit this type of dominance. Indeed, Mendel himself was aware that dominance is not universal, because he observed that a pea plant heterozygous for long and short flowering times had a flowering time that was intermediate between those of its homozygous parents. This situation, in which the heterozygote is intermediate in phenotype between the two homozygotes, is termed incomplete dominance. Dominance can be understood in regard to how the phenotype of the heterozygote relates to the phenotypes of the homozygotes. Complete G7. The 8% allele is dominant A over the A allele. Has flowers that are the same color as the A2 homozygote white, then the A2 allele is completely dominant, and white is dominant over red. When the heterozygote falls in between the phenotypes of the two homozygotes, dominance is incomplete. With incomplete dominance, the heterozygote need not be exactly intermediate. Pink in our example between the two homozygotes, it might be a slightly lighter shade of red or a slightly pink shade of white. As long as the heterozygote's phenotype can be differentiated and falls within the range of the two homozygotes, dominance is incomplete. The important thing to remember about dominance is that it affects the phenotype that genes produce, but not the way in which genes are inherited. Another type of interaction between alleles is codominance, in which the phenotype of the heterozygote is not intermediate between the phenotypes of the homozygotes. Rather, the heterozygote simultaneously expresses the phenotypes of both homozygotes. An example of codominance is seen in the MN blood types. The MN locus codes for one of the types of antigens on red blood cells. Unlike antigens 4 into the ABO and Rh blood groups, which also code for red blood cell antigens, 4 and MN antigens do not elicit a strong immunological reaction, and therefore the MN blood types are not routinely considered in blood transfusions. At the MN locus, there are two alleles, the LM allele, which codes for the M antigen, and the lane allele, which codes for the N antigen. Homozygotes with genotype LMLM express the M antigen on their red blood cells and have the M blood type. Homozygotes with genotype LNLN express the N antigen and have the N blood type. Heterozygotes with genotype LMLN exhibit codominance and express both the M and the N antigens. They have blood type MN. The differences between dominance, incomplete dominance, and codominance are summarized in table 1. Incomplete dominance. Y. Alg. If the phenotype of the heterozygote the type of dominance that a character exhibits frequently depends on the level of the phenotype examined. An example is cystic fibrosis, one of the more common genetic disorders found in Caucasians and usually considered to be a recessive disease. People who have cystic fibrosis produce large quantities of thick, sticky mucus, which plugs up the airways of the lungs and clogs the ducts leading from the pancreas to the intestine, causing frequent respiratory infections and digestive problems. Even with medical treatment, patients with cystic fibrosis suffer chronic, life-threatening medical problems. The gene responsible for cystic fibrosis resides on the long arm of chromosome 7. It encodes the protein termed cystic fibrosis transmembrane conductance regulator, mercifully abbreviated CFTR, which acts as a gate in the cell membrane and regulates the movement of chloride ions into and out of the cell. Patients with cystic fibrosis have a mutated, dysfunctional form of CFTR that causes the channel to stay closed, and so chloride ions build up in the cell. This buildup causes the formation of thick mucus and produces the symptoms of the disease. Most people have 2 copies of the normal allele for CFTR and produce only functional CFTR protein. Those with cystic fibrosis possess 2 copies of the mutated CFTR allele and produce only the defective CFTR protein. Heterozygotes with 1 normal and 1 defective CFTR allele produce both functional and defective CFTR protein. Thus, at the molecular level, the alleles for normal and defective CFTR are codominant because both alleles are expressed in the heterozygote. However, because one normal allele produces enough functional CFTR protein to allow normal chloride transport, the heterozygote exhibits no adverse effects, and the mutated CFTR allele appears to be recessive at the physiological level. In summary, several important characteristics of dominance should be emphasized. First, dominance is a result of interactions between genes at the same locus. In other words, dominance is allelic interaction. Second, dominance does not alter the way in which the genes are inherited. It only influences the way in which they are expressed as a phenotype. The allelic interaction that characterizes dominance is therefore interaction between the products of the genes. Finally, dominance is frequently in the eye of the beholder, meaning that the classification of dominance depends on the level at which the phenotype is examined. As we saw with cystic fibrosis, an allele may exhibit codominance at one level and be recessive at another level. Lethal alleles. In 1905, Lucian Quine reported a peculiar pattern of inheritance in mice when he mated 2 yellow mice. Approximately either 2/3 offspring were yellow and percent were non-yellow. When he test crossed the yellow mice, he found that all were heterozygous. He was never able to obtain a yellow mouse that bred true. There was a great deal of discussion about Quine's results among his colleagues, but it was eventually realized that the yellow allele must be lethal when homozygous figure 3. A lethal allele is one that causes death at an early stage of development, often before birth, and so some genotypes may not appear among the progeny. P generation. Yellow yellow. QX. YY. Another example of a lethal allele, originally described by Erwin Bauer in 1907, is found in snapdragons. The Urea strain in these plants has yellow leaves. When 2 plants with yellow leaves are crossed, 2/3 of the progeny have yellow leaves and 1/3 have green leaves. When green is crossed with green, all the progeny have green leaves. However, when yellow is crossed with green, percent of the progeny are green and percent are yellow, confirming that all yellow leaf snapdragons are heterozygous. A2, 1 ratio is almost always produced by recessive lethal allele, so observing this ratio among the progeny of a cross between individuals with the same phenotype is a strong clue that one of the alleles is lethal. In both of these examples, the lethal alleles are recessive because they cause death only in homozygotes. Unlike its effect on survival, the effect of the allele on color is dominant. In both mice and snapdragons, a single copy of the allele in the heterozygote produces a yellow color. Lethal alleles also can be dominant, in this case, homozygotes and heterozygotes for the allele die. Truly dominant lethal alleles cannot be transmitted unless they are expressed after the onset of reproduction, as in Huntington disease. Multiple alleles. Most of the genetic systems that we have examined so far consist of 2 alleles. In Mendel's peas, for instance, one allele coded for round seeds and another for wrinkled seeds. In cats, one allele produced a black coat and another produced a gray coat. For some loci, more than 2 alleles are present within a group of individuals. The locus has multiple alleles. Multiple alleles may also be referred to as an allelic series. Although there may be more than 2 alleles present within a group, the genotype of each diploid individual still consists of only 2 alleles. The inheritance of characteristics encoded by multiple alleles is no different from the inheritance of characteristics encoded by 2 alleles, except that a greater variety of genotypes and phenotypes are possible. Duck feather patterns. An example of multiple alleles is seen at a locus that determines the feather pattern of mallard ducks. One allele M produces the wild-type mallard pattern. A second allele Mr. produces a different pattern called restricted, and a third allele MD produces a pattern termed dusky. In this allelic series, restricted is dominant over mallard and dusky, and mallard is dominant over dusky. Mr. greater than M greater than MD. The 6 genotypes possible with these 3 alleles and the resulting phenotypes are genotype phenotype MRMR restricted, MRM restricted, MRMD restricted, and mallard MMD, mallard MD, MD dusky. In general, the number of genotypes possible will be n1, 2, where n equals the number of different alleles at a locus. Working crosses with multiple alleles is no different from working crosses with 2 alleles. Mendel's principle of segregation still holds, as shown in the cross between a restricted duck and a mallard duck, figure 4. For Mendel's principle of segregation applies to crosses with multiple alleles. In this example, 3 alleles determine the type of plumage in mallard ducks. MR restricted greater than M mallard greater than M9 dusky. IY. The ABO blood group. Another multiple allele system is the locus for the ABO blood group. This locus determines your ABO blood type. And, like the MN locus, codes for antigens on red blood cells. The 3 common alleles for the ABO blood group locus are I4, which codes for the A antigen, I8, which codes for the B Antigen, and I, which codes for no antigen, 0. We can represent the dominance relations among the ABO alleles as follows. 1A greater than I, IB greater than I, A equals IB. The I and IB alleles are both dominant over I and are codominant with each other. The AB phenotype is due to the presence of an I hash allele and IB allele, which results in the production of A and B antigens on red blood cells. An individual with genotype B produces neither antigen and has blood type O. The 6 common genotypes of this locus and their phenotypes are shown in figure 5A. Antibodies are produced against any foreign antigens. See figure 5A. For instance, a person having blood type O produces B antibodies because the B antigen is foreign. A person having blood type B produces antibodies, and someone having blood type AB produces neither nor B antibodies because neither nor B antigen is foreign. A person having blood type O possesses no A or B antigens. Consequently, that person produces both antibodies and B antibodies. The presence of antibodies against foreign ABO antigens means that successful blood transfusions are possible only between persons with certain compatible blood types. Figure 5B. A. Phenotype, genotype, antigen, antibodies, blood type made by body. The inheritance of alleles of the ABO locus can be illustrated by a paternity suit involving the famous movie actor Charlie Chaplin. In 1941, Chaplin met a young actress named Joan Barry, with whom he had an affair. The affair ended in February 1942, but 20 months later, Barry gave birth to a baby girl and claimed that Chaplin was the father. Barry then sued for child support. At this time, blood typing had just come into widespread use, and Chaplin's attorneys had Chaplin, Barry, and the child blood typed. Barry had blood type A, her child had blood type B, and Chaplin had blood type O. Could Chaplin have been the father of Barry's child? Your answer should be no. Joan Barry had blood type A, which can be produced by either genotype A4 or I4I. Her baby possessed blood type B, which can be produced by either genotype IB, IB, or I. The baby could not have inherited the IB allele from Barry. Barry could not carry an IB allele if she were blood type A. Therefore, the baby must have inherited the I allele from her. Barry must have had genotype II, and the baby must have had genotype B because the baby girl inherited her allele from Barry. She must have inherited the allele from her father. With blood type O, produced only by genotype B, Chaplin could not have been the father of Barry's child. In the course of the trial to settle the paternity suit, three pathologists came to the witness stand and declared that it was genetically impossible for Chaplin to have fathered the child. Nevertheless, the jury ruled that Chaplin was the father and ordered him to pay child support and Barry's legal expenses. Gene interaction. In the dihybrid crosses that we examined, each locus had an In the dihybrid crosses that we examined, each locus had an independent effect on the phenotype. When Mendel crossed a homozygous round in yellow plant RRYY with a homozygous wrinkled in green plant RRYY and then self-fertilized the F1, he obtained F2 progeny in the following proportions: ERY round, yellow; ERYY round, green; ERRY underscore wrinkled, yellow; SRYY wrinkled, green. In this example, the genes show two kinds of independence. First, the genes of each locus are independent in their assortment in meiosis, which is what produces the 9:3:3:1 ratio of phenotypes in the progeny, in accord with Mendel's principle of independent assortment. Second, the genes are independent in their phenotypic expression. The R and R alleles affect only the shape of the seed and have no influence on the color of the endosperm. The Y and Y alleles affect only color and have no influence on the shape of the seed. Frequently, genes exhibit independent assortment but do not act independently in their phenotypic expression. Instead, the effects of genes at one locus depend on the presence of genes at other loci. This type of interaction between the effects of genes at different loci, genes that are not allelic, is termed gene interaction. With gene interaction, the products of genes at different loci combine to produce new phenotypes that are not predictable from a single locus effects alone. In our consideration of gene interaction, we'll focus primarily on interaction between the effects of genes at two loci, although interactions among genes at 3, 4, or more loci are common. Gene interaction that produces novel phenotypes. Let's first examine gene interaction in which genes at two loci interact to produce a single characteristic. Fruit color in the pepper capsicum annuum is determined in this way. This plant produces peppers in one of four colors: red, brown, yellow, or green. If a homozygous plant with red peppers is crossed with a homozygous plant with green peppers, all the F1 plants have red peppers. Figure 6a. When the F1 are crossed with one another, the F2 are in a ratio of 9 red, 3 brown, 3 yellow, 1 green. Figure 6b. This dihybrid ratio is produced by a cross between two plants that are both heterozygous for two loci RRCC x RRCC. In peppers, a dominant allele R at the first locus produces a red pigment. The recessive allele R at this locus produces no red pigment. A dominant allele C at the second locus causes decomposition of the green pigment chlorophyll. The recessive allele C allows chlorophyll to persist. The genes of the two loci then interact to produce the color seen in F2 peppers. Genotype phenotype RC red, RCC brown, RL underscore yellow RREC green. To illustrate how Mendel's rules of heredity can be used to understand the inheritance of characteristics determined by gene interaction, let's consider a test cross between an F1 plant from the cross in figure 6 RRCC and a plant with green peppers RRCC. For independent loci, we can work this cross by breaking it down into two simple crosses. At the first locus, the heterozygote RR is crossed with a homozygote RR. This cross produces %RR and %2RR progeny. Similarly, at the second locus, the heterozygous genotype CC is crossed with a homozygous genotype CC, producing %CC and %2CC progeny. In accord with Mendel's principle of independent assortment, these single locus ratios can be combined by using the multiplication rule. The probability of obtaining the genotype RRCC is the probability of RR, 1/2 multiplied by the probability of CC, 1/2 4%. The probability of each progeny genotype resulting from the test cross is progeny probability RL. Genotype of each locus probability phenotype. RRCCO equals Y red peppers reacts O equals U brown peppers RRCEO equals Y yellow peppers EXO equals Y green peppers. When you work problems with gene interaction, it is especially important to determine the probabilities of single locus genotypes and to multiply the probabilities of genotypes, not phenotypes, because the phenotypes cannot be determined without considering the effects of the genotypes at all the contributing loci. Another example of gene interaction that produces novel phenotypes is seen in the genes that determine comb shape in chickens. The comb is the fleshy structure found on the head of a chicken. Genes at two loci R and P interact to determine the four types of combs shown in figure 7. One chicken's comb is determined by gene interaction between two local. A walnut comb is produced when there is a dominant allele at each of two loci R underscore P underscore. B rose comb occurs when there is a dominant allele only at the first locus R underscore PP. C AP comb occurs when there is a dominant allele only at the second locus PPR underscore. D single comb is produced by the presence of only recessive alleles at both loci RR PP. A walnut comb is produced when at least one dominant allele R is present at the first locus and at least one dominant allele P is present at the second locus. Genotype R underscore P underscore. A chicken with at least one dominant allele at the first locus and two recessive alleles at the second locus. Genotype R underscore PP possesses a rose comb. If two recessive alleles are present at the first locus and at least one dominant allele is present at the second, genotype RRP underscore, the chicken has a P comb. Finally, if two recessive alleles are present at both loci RRPP, the bird has a single comb. Gene interaction with epistasis. Sometimes the effect of gene interaction is that one gene masks hides the effect of another gene at a different locus, a phenomenon known as epistasis. This phenomenon is similar to dominance, except that dominance entails the masking of genes at the same locus, allelic genes. In epistasis, the gene that does the masking is called the epistatic gene. The gene whose effect is masked is a hypostatic gene. Epistatic genes may be recessive or dominant in their effects. Recessive epistasis. Recessive epistasis is seen in the genes that determine coat color in Labrador retrievers. These dogs may be black, brown, or yellow. Their different coat colors are determined by interactions between genes at two loci, although a number of other loci also help to determine coat color. One locus determines the type of pigment produced by the skin cells. A dominant allele B codes for black pigment, whereas a recessive allele B codes for brown pigment. Alleles of the second locus affect the deposition of the pigment in the shaft of the hair. Allele E allows dark pigment, black or brown, to be deposited, whereas the recessive allele E prevents the deposition of dark pigment, causing the hair to be yellow. The presence of genotype E at the second locus therefore masks the expression of the black and brown alleles of the first locus. The genotypes that determine coat color and the phenotypes are genotype phenotype. BE lac. If we cross a black Labrador homozygous for the dominant alleles with a yellow Labrador homozygous for the recessive alleles and then intercross the F1, we obtain progeny in the F2 9 3 4 ratio. PBXBB. Black bellow. Notice that yellow dogs can carry alleles for either black or brown pigment, but these alleles are not expressed in their coat color. Institute for Advanced Studies, Jodhpur 17. In this example of gene interaction, allele E is epistatic to B and B because E masks the expression of the alleles for black and brown pigments, and alleles B and B are hypostatic to E. In this case, E is a recessive epistatic allele, because 2 copies of E must be present to mask the black and brown pigments. Dominant epistasis. Dominant epistasis is seen in the interaction of two loci that determine fruit color in summer squash, which is commonly found in one of three colors: yellow, white, or green. When a homozygous plant that produces white squash is crossed with a homozygous plant that produces green squash and the F1 plants are crossed with each other, the following results are obtained. P plants with white squash less than green squash. I. L. F plants with white squash. L. L. Intercross F. 3 plants with white squash, 3 plants with yellow squash, Y. F plants with green squash. How can gene interaction explain these results? In the F2, 12/16% of the plants produce white squash, and 3/16 plus 1/16 equals 4/16 equals 1/4 of the plants produce squash having color. This outcome is the familiar 3:1 ratio produced by cross between two heterozygous individuals, which suggests that a dominant allele at one locus inhibits the production of pigment, resulting in white progeny. If we use the symbol W to represent the dominant allele that inhibits pigment production, then genotype W underscore inhibits pigment production and produces white squash, whereas WW allows pigment and results in colored squash. Among those WWF2 plants with pigmented fruit, we observe 3/16 yellow and 1/16 green, a 3:1 ratio. This outcome is because the second locus determines the type of pigment produced in the squash, with yellow Y underscore dominant over green YY. This locus is expressed only in WW plants, which lack the dominant inhibitory allele W. We can assign the genotype WWY underscore to plants that produce yellow squash and the genotype WWYY to plants that produce green squash. The genotypes and their associated phenotypes are white squash, WYY white squash, WW yellow squash, WYY green squash. Allele W is epistatic to Y and Y. It suppresses the expression of these pigment-producing genes. W is a dominant epistatic allele because, in contrast with E and Labrador Retriever coat color, a single copy of the allele is sufficient to inhibit pigment production. Summer squash provides us with a good opportunity for considering how epistasis often arises when genes affect a series of steps in a biochemical pathway. Yellow pigment in the squash is most likely produced in a two-step biochemical pathway, figure 8. A colorless white compound designated in figure 8 is converted by enzyme into green compound B, which is then converted into compound C by enzyme 2. Compound C is the yellow pigment in the fruit. Plants with the genotype WW produce enzyme I and may be green or yellow, depending on whether enzyme 2 is present. When allele Y is present at a second locus, enzyme 2 is produced and compound B is converted into compound C, producing a yellow fruit. When two copies of Y, which does not encode a functional form of enzyme 2, are present, squash remain green. The presence of W at the first locus inhibits the conversion of compound into compound B. Plants with genotype W underscore do not make compound B and the fruit remains white, regardless of which alleles are present at the second locus. Many cases of epistasis arise in this way. A gene such as W that has an effect on an early step in a biochemical pathway will be epistatic to genes such as Y and Y that affect subsequent steps because the effect of the enzyme in the later step depends on the product of the earlier reaction. Plants with genotype underscore produce ANSI I MWHE it converts compound A. Let's consider one more detailed example of epistasis. Albinism is the absence of pigment and is a common genetic trait in many plants and animals. Pigment is almost always produced through a multi-step biochemical pathway. Thus, albinism may entail gene interaction. Robert T. Dillon and Amy R. Weddington found that albinism in the common freshwater snail Physa heterostropha can result from the presence of either of two recessive alleles at two different loci. Inseminated snails were collected from a natural population and placed in cups of water, where they laid eggs. Some of the eggs hatched into albino snails. When two albino snails were crossed, all of the F1 were pigmented. On intercrossing the F1, the F2 and 9/16 consisted of pigmented snails and 7/16 albino snails. How did this 9:7 ratio arise? The 9:7 ratio seen in the F2 snails can be understood as a modification of the 9:3:1 ratio obtained when two individuals heterozygous for two loci are crossed. The 9:7 ratio arises when dominant alleles at both loci A underscore B underscore ENSA O1 DCTIE on alpha RNs MYI produce pigmented snails. Any other genotype produces albino snails. A second point is that in the examples that we have considered, the phenotypic proportions were always in 16 because, in all the crosses, pairs of alleles PAAB segregated at two independently assorting loci. B. Albino greater than albino probability of inheriting one of the two alleles at a locus is percent. J. Because there are two loci, each with two alleles, the probability of inheriting any particular combination of genes is 2n equals 1/16. For a trihybrid cross, the progeny proportion should be in 60/4 because 1/2 equals 1/64. In general, the progeny proportion should be in fractions of 1/2 2n, where n equals the number of loci with two alleles. Segregating in the cross. FAABB. Pigmented. I. Intercross. B by enzyme I and after compound B has been converted into compound C by enzyme 2. At least 12:3:1 dominant allele at the first locus is required and 7 to produce enzyme I. Similarly, at least 1:6:1 dominant allele B at the second locus is required 15:01 to produce enzyme 2. Albinism arises from the absence of compound C, which may happen in 13:3. Three ways. First, two recessive alleles at the first locus genotype AAB underscore may prevent the production of enzyme I, and so compound B is never produced. Second, two recessive alleles at the second locus genotype A underscore BB may prevent the production of enzyme L. In this case, compound B is never converted into compound C. Third, two recessive alleles may be present at both loci A, A, B, B, causing the absence of both enzyme I and enzyme L. In this example of gene interaction, A is epistatic to B, and B is epistatic to A. Both are recessive epistatic alleles because the presence of two copies of either allele or B is necessary to suppress pigment production. This example differs from suppression of coat color in Labrador retrievers in that recessive alleles at either of two loci are capable of suppressing pigment production in the snails, whereas recessive alleles at a single locus suppress pigment expression in labs. Interpreting ratios produced by gene interaction. A number of modified ratios that result from gene interaction are shown in table 5.2. Each of these examples represents a modification of the basic 9:3:1 dihybrid ratio. In interpreting the genetic basis of modified ratios, we should keep several points in mind. First, the inheritance of the genes producing these characteristics is no different from the inheritance of genes coding for simple genetic characters. Mendel's principles of segregation and independent assortment still apply. Each individual possesses two alleles at each locus, which separate in meiosis, and genes of the different loci sort independently. The only difference is in how the products of the genotypes interact to produce the phenotype. Thus, we cannot consider the expression of genes at each locus separately, but must take into consideration how the genes at different loci interact. Retrievers. Dominant epistasis. 7 duplicate recessive epistasis. Duplicate interaction. Duplicate dominant epistasis. Dominant TD recessive epistasis. Reading across, each row gives the phenotypic ratios of progeny from a divigrid. How do we know whether different mutations that affect a characteristic occur at the same locus or allelic or at different loci? In fruit flies, for example, white is an X-linked mutation that produces white eyes instead of the red eyes found in wild-type flies. Apricot is an X-linked recessive mutation that produces light orange colored eyes. Do the white and apricot mutations occur at the same locus or at different loci? We can use the complementation test to answer this question. To carry out a complementation test, parents that are homozygous for different mutations are crossed, producing offspring that are heterozygous. If the mutations are allelic occur at the same locus, then the heterozygous offspring have only muted alleles and exhibit a muted phenotype. IAXBIIAOBI. IA muted phenotype. If, on the other hand, the mutations occur at different loci, each of the homozygous parents possesses wild-type genes at the other locus, OBB and AABB, so the heterozygous. Institute for Advanced Studies, Job for 19. Caloid and squash albinism in snails. Offspring inherit a mutant and a wild-type allele at each locus. In this case, the mutations complement each other and the heterozygous offspring have a wild-type phenotype. A BTX at B. AB at B. AB as. Complementation occurs when an individual possessing two mutant genes has a wild-type phenotype and is an indicator that the mutations are non-allelic genes. When the complementation test is applied to white and apricot mutations, all of the heterozygous offspring have light-colored eyes, demonstrating that white and apricot are produced by mutations that occur at the same locus and are allelic. Interaction between sex and heredity. In previous section, we considered characteristics encoded by genes located on the sex chromosomes and how their inheritance differs from the inheritance of traits encoded by autosomal genes. Now we will examine additional influences of sex, including the effect of the sex of an individual on the expression of genes on autosomal chromosomes, characteristics determined by genes located in the cytoplasm, and characteristics for which the genotype of only the maternal parent determines the phenotype of the offspring. Finally, we look at situations in which the expression of genes on autosomal chromosomes is affected by the sex of the parent from whom they are inherited. Sex influence and sex-limited characteristics. Sex influence characteristics are determined by autosomal genes and are inherited according to Mendel's principles, but they are expressed differently in males and females. In this case, a particular trait is more readily expressed in one sex. In other words, the trait has higher penetrance in one of the sexes. For example, the presence of a beard on some goats is determined by an autosomal gene PP that is dominant in males and recessive in females. In males, a single allele is required for the expression of this trait. Both the homozygote BPBY and the heterozygote B have beards, whereas the B asterisk B male is beardless. In contrast, females require two alleles in order for this trait to be expressed. The homozygote B asterisk BP has a beard, whereas the heterozygote BB and the other homozygote BB are beardless. The key to understanding the expression of the bearded gene is to look at the heterozygote. In males for which the presence of a beard is dominant, the heterozygous genotype produces a beard, but in females for which the presence of a beard is recessive and its absence is dominant, the heterozygous genotype produces a goat without a beard. A. D trademark P generation bearded 9 beardless 6. EOTQX asterisk. 9 genes that encode sex influence traits are inherited according to Mendel's principles but are expressed differently in males and females. Figure 9 illustrates a cross between a beardless male B underscore D underscore and a bearded female BBY. The alleles separate into gametes according to Mendel's principle of segregation, and all the F1 are heterozygous B underscore BP. Because the trait is dominant in males and recessive in females, all the F1 males will be bearded, and all the F1 females will be beardless. When the F1 are crossed with one another, percent of the F2 progeny are B asterisk BP, percent or B asterisk B underscore, and a percent B underscore D underscore, figure 9b. Because male heterozygotes are bearded, percent of the males in the F2 possess beards. Because female heterozygotes are beardless, only percent of the females in F2 are bearded. An example of a sex influence characteristic in humans is pattern baldness, in which hair is lost prematurely from the front to the top of the head. Pattern baldness is an autosomal character believed to be dominant in males and recessive in females, just like beards in goats. Contrary to a popular misconception, a man does not inherit pattern baldness from his mother's side of the family, which would be the case if the character were X-linked, but it isn't. Pattern baldness is autosomal. Men and women can inherit baldness from either their mothers or their fathers. Men require only a single allele for baldness to become bald, whereas women require two alleles for baldness, and so pattern baldness is much more common among men. Furthermore, pattern baldness is expressed weakly in women. Those with the trait usually have only a mild thinning of the hair, whereas men frequently lose all the hair on the top of the head. The expression of the allele for pattern baldness is clearly enhanced by the presence of male sex hormones. Males who are castrated at an early age rarely become bald, but castration is not a recommended method for preventing baldness. An extreme form of sex influence inheritance. An extreme form of sex influence inheritance, a sex-limited characteristic is encoded by autosomal genes that are expressed in only one sex. The trait has zero penetrance in the other sex. In domestic chickens, some males display a plumage pattern called cock feathering. Other males and all females display a pattern called hen feathering. Cock feathering is an autosomal recessive trait that is sex-limited to males. Because the trait is autosomal, the genotypes of males and females are the same, but the phenotypes produced by these genotypes differ in males and females. Genotype male phenotype female phenotype. HH hen feathering HH hen feathering HH cock feathering hen feathering. An example of a sex-limited characteristic in humans is male-limited precocious puberty. There are several types of precocious puberty in humans, most of which are not genetic. Male-limited precocious puberty, however, results from an autosomal dominant allele P that is expressed only in males. Females with a gene are normal in phenotype. Males with precocious puberty undergo puberty at an early age, usually before the age of 4. At this time, the penis enlarges, the voice deepens, and pubic hair develops. There is no impairment of sexual function. Affected males are fully fertile. Most are short as adults because the long bones stop growing after puberty. Because the trait is rare, affected males are usually heterozygous PP. A male with precocious puberty who mates with a woman who has no family history of this condition will transmit the allele for precocious puberty to percent of the children, figure 10a, but it will be expressed only in the sons. If one of the heterozygous daughters PP mates with a male who has normal puberty PP, of the sons will exhibit precocious puberty, figure 10b. Thus a sex-limited characteristic can be inherited from either parent, although the trait appears in only one sex. Thus a sex-limited characteristic can be inherited from either parent, although the trait appears in only one sex. The results of molecular studies reveal that the underlying genetic defect in male-limited precocious puberty affects the receptor for luteinizing hormone, LH. This hormone normally attaches to receptors found on certain cells of the testes and stimulates these cells to testosterone. During normal puberty in males, high levels of LH stimulate the increased production of testosterone, which, in turn, stimulates the anatomical and physiological changes associated with puberty. The P allele for precocious puberty codes for a defective LH receptor, which stimulates testosterone production even in the absence of LH. Boys with this allele produce high levels of testosterone at an early age, when levels of LH are low. Defective LH receptors are also found in females who carry the precocious puberty gene, but their presence does not result in precocious puberty because additional hormones are required along with LH to induce puberty in girls. Institute for Advanced Studies, Job for 21. D gene mapping methods, linkage maps, tetrad analysis, mapping with molecular markers, mapping by using somatic cell hybrids, development of mapping population in plants. Linkage and independent assortment. We have introduced Mendel's principles of segregation and independent assortment. Let's take a moment to review these two important concepts. The principle of segregation states that each diploid individual possesses two alleles that separate in meiosis, with one allele going into each gamete. The principle of independent assortment provides additional information about the process of segregation. It tells us that the two alleles separate independently of alleles at other loci. The independent separation of alleles produces recombination, the sorting of alleles into new combinations. Consider a cross between individuals homozygous for two different pairs of alleles, AABB-XAABB. The first parent, AABB, produces gametes with alleles AB, and the second parent, AABB, produces gametes with the alleles AB, resulting in F1 progeny with genotype AABB, figure 1. Recombination means that, when one of the F1 progeny reproduces, the combination of alleles in its gametes may differ from the combinations in the gametes of its parents. In other words, the F the first of may produce gametes with alleles A flat or AB in addition to gametes with AB or AB. P generation H. AIBB-XAABB a game of A formula UNL. Mendel derived his principles of segregation and independent assortment by observing progeny of genetic process, but he had no idea what biological processes produced these phenomena. In 1903, Walter Sutton proposed a biological basis for Mendel's principles, called the chromosome theory of heredity. This theory holds that genes are found on chromosomes. Let's restate Mendel's two principles in terms of the chromosome theory of heredity. The principle of segregation states that each diploid individual possesses two alleles for a trait, each of which is located at the same position, or locus, on each of the two homologous chromosomes. These chromosomes segregate in meiosis, with each gamete receiving one homolog. The principle of independent assortment states that, in meiosis, each pair of homologous chromosomes assorts independently of other homologous pairs. With this new perspective, it is easy to see that the number of chromosomes in most organisms is limited and that there are certain to be more genes than chromosomes, so some genes must be present on the same chromosome and should not assort independently. Genes located close together on the same chromosome are called linked genes and belong to the same linkage group. As we've said, linked genes travel together during meiosis, eventually arriving at the same destination, the same gamete, and are not expected to assort independently. However, all of the characteristics examined by Mendel in piece to display independent assortment, and after the rediscovery of Mendel's work, the first genetic characteristics studied in other organisms also seem to assort independently. How could genes be carried on a limited number of chromosomes and yet assort independently? The apparent inconsistency between the principle of independent assortment and the chromosome theory of heredity soon disappeared, as biologists began finding genetic characteristics that did not assort independently. One of the first cases was reported in Sweet Peas by William Bateson, Edith Rebecca Saunders, and Reginald C. Punnett in 1905. They crossed a homozygous strain of peas having purple flowers and long pollen grains with a homozygous strain having red flowers and round pollen grains. All the F1 had purple flowers and long pollen grains, indicating that purple was dominant over red and long was dominant over round. When they intercrossed the F1, the resulting F2 progeny did not appear in the 9:3:3:1 ratio expected with independent assortment, figure 2. An excessive F2 plants had purple flowers and long pollen or red flowers and round pollen, the parental phenotypes. Although Bateson, Saunders, and Punnett were unable to explain these results, we now know that the two loci that they examined lie close together on the same chromosome and therefore do not assort independently. Tilde. Red now flowers. Round pollen. A. Genes on the same chromosome are like passengers on a charter bus. They travel together and ultimately arrive at the same destination. However, genes occasionally switch from one homologous chromosome to another through the process of crossing over, figure 3. Crossing over produces recombination. It breaks up the associations of genes imposed by linkage. As will be discussed later, genes located on the same chromosome can exhibit independent assortment if they are far enough apart. In summary, linkage adds a further complication to interpretations of the results of genetic crosses. With an understanding of how linkage affects heredity, we can analyze crosses for linked genes and successfully predict the types of progeny that will be produced. Late purple metaphase crossing. Over. Notation for crosses with linkage. In analyzing crosses with linked genes, we must know not only the genotypes of the individuals crossed, but also the arrangement of the genes on the chromosomes. To keep track of this arrangement, we will introduce a new system of notation for presenting crosses with linked genes. Consider a cross between an individual homozygous for dominant alleles at two linked loci and another individual homozygous for recessive alleles at those loci. Previously, we would have written these genotypes as AABB-XAABB. For linked genes, however, it's necessary to write out the specific alleles as they are arranged on each of the homologous chromosomes. ABABABAB. In this notation, each line represents one of the two homologous chromosomes in the first parent of the cross. Each homologous chromosome contains A and B alleles. In the second parent, each homologous chromosome contains A and B alleles. Inheriting one chromosome from each parent, the F1 progeny will have the following genotype. AB. Here, the importance of designating the alleles on each chromosome is clear. One chromosome has the two dominant alleles A and B, whereas the homologous chromosome has the two recessive alleles A and B. The notation can be simplified by drawing only a single line, with the understanding that genes located on the same side of the line lie on the same chromosome. ABAB. This notation can be simplified further by separating the alleles on each chromosome with a slash. ABAB. Remember that the two alleles at a locus are always located on different homologous chromosomes and therefore must lie on opposite sides of the line. Consequently, we would never write the genotypes as AA, BB, because the alleles A and A can never be on the same chromosome. It is also important to always keep the same order of the genes on both sides of the line. Thus, we should never write ABBA, because this would imply that alleles A and B are allelic at the same locus. Complete linkage compared with independent assortment. We will first consider what happens to genes that exhibit complete linkage, meaning that they are located on the same chromosome and do not exhibit detectable crossing over. Genes rarely exhibit complete linkage, but without the complication of crossing over, the effect of linkage can be seen more clearly. We will then consider what happens when genes assort independently. Finally, we will consider the results obtained if the genes are linked but exhibit some crossing over. A test cross reveals the effects of linkage. For example, if a heterozygous individual is test crossed with a homozygous recessive individual AABB-XAABB, whatever alleles are present in the gametes contributed by the heterozygous parent will be expressed in the phenotype of the offspring, because the homozygous parent could not contribute dominant alleles that might mask them. Consequently, traits that appear in the progeny reveal which alleles were transmitted by the heterozygous parent. Institute for Advanced Studies, Jodhpur 23. Consider a pair of linked genes in tomato plants. One pair affects the type of leaf. An allele for mottled leaves M is recessive to an allele that produces normal leaves M. Nearby on the same chromosome is another locus that determines the height of the plant. An allele for dwarf T is recessive to an allele for tall T. Testing for linkage can be done with a test cross, which requires a plant heterozygous for both traits. A geneticist might produce this heterozygous plant by crossing a variety of tomato that is homozygous for normal leaves and tall height with a variety that is homozygous for mottled leaves and dwarf height. PMDMD. MDTMD. FMD. MD. The geneticist would then use these F1 heterozygotes in a test cross, crossing them with plants homozygous for mottled leaves and dwarf height. MDMD. MDMD. The results of this test cross are diagrammed in figure 4a. During gamete formation, the heterozygote produces two types of gametes, some with the MD chromosome and others with the MD chromosome. Because no crossing over occurs, these gametes are the only types produced by the heterozygote. Notice that these gametes contain only combinations of alleles that were present in the original parents, either the allele for normal leaves together with the allele for tall height M and D, or the allele for mottled leaves together with the allele for dwarf height M and D. Gametes that contain only original combinations of alleles present in the parents are non-recombinant gametes, or parental gametes. The homozygous parent in the test cross produces only one type of gamete. It contains chromosome MD in pairs with one of the two gametes generated by the heterozygous parent. See figure 4a. Two types of progeny result. Half have normal leaves and are tall M, MD, and half have mottled leaves and are dwarf. These progeny display the original combinations of traits present in the P generation and are non-recombinant progeny, or parental progeny. No new combinations of the two traits, such as normal leaves with dwarf or mottled leaves with tall, appear in the offspring because the genes affecting the two characteristics are completely linked and are inherited together. New combinations of traits could. IT genes are completely linked, no crossing over. Arise only if the linkage between M and D or between M and D were broken. These results are distinctly different from the results that are expected when genes assort independently. Figure 4b. With independent assortment, the heterozygous plant MMDD would produce 4 types of gametes. 2 non-recombinant gametes containing the original combinations of alleles MD and MD, and 2 gametes containing new combinations of alleles MD and MD. Gametes with new combinations of alleles are called recombinant gametes. With independent assortment, non-recombinant and recombinant gametes are produced in equal proportions. These 4 types of gametes join with a single type of gamete produced by the homozygous parent of the test cross to produce 4 kinds of progeny in equal proportions. See figure 4b. The progeny with new combinations of traits formed from recombinant gametes are termed recombinant progeny. B. If genes astral independently. A test cross reveals the effects of linkage. Results of a test cross. For 2 loci in tometes that determine leaf type and plant height. In summary, a test cross in which one of the plants is heterozygous for 2 completely linked genes yields 2 types of progeny, each type displaying one of the original combinations of traits present in the P generation. Independent assortment, in contrast, produces 2 types of recombinant progeny and 2 types of non-recombinant progeny in equal proportions. SR confusion with independent ONU. 20. Crossing over with linked genes. Linkage is rarely complete. Usually, there is some crossing over between linked genes, interval linkage producing new combinations of traits. Let's see how this occurs. Theory: the effect of crossing over on the inheritance of 2 linked genes is shown in figure 5. Crossing over, which takes place in prophase of meiosis, is the exchange of genetic material between non-sister chromatids. After a single crossover has taken place, the 2 chromatids that did not participate in crossing over are unchanged. Gametes that receive these chromatids are non-recombinants. The other 2 chromatids, which did participate in crossing over, now contain new combinations of alleles. Gametes that receive these chromatids are recombinants. At no crossing over. Homologous chromosomes ER, no crossing pair in prophase. In the genes that code for leaf type and plant height. Assume now that these genes are linked and that some crossing over takes place between them. Suppose a geneticist carried out the test cross outlined earlier. When crossing over takes place between the genes for leaf type and height, 2 of the 4 gametes produced will be recombinants. When there is no crossing over, all 4 resulting gametes will be non-recombinants. Thus, overall, the majority of gametes will be non-recombinants. These gametes then unite with gametes produced by the all resulting chromosomes in AT __ gametes have original allele equals _ combinations that are non-recombinants. L _ 001. And in this case, half of the resulting gametes will have L unchanged chromosomes, non-recombinants. Slash. Dot and half will have 5 crossing over produces half non-recombinant gametes and half recombinant gametes. For each meiosis in which a single crossover takes place, then 2 non-recombinant gametes and 2 recombinant gametes will be produced. This result is the same as that produced by independent assortment. So, when crossing over between 2 loci takes place in every meiosis, it is impossible to determine whether the genes were linked and crossing over took place or whether the genes are on different chromosomes. For closely linked genes, crossing over does not take place in every meiosis. In meiosis in which there is no crossing over, only non-recombinant gametes are produced. In meiosis in which there is a single crossover, half the gametes are recombinants and half are non-recombinants because a single crossover only affects 2 of the 4 chromatids, so the total percentage of recombinant gametes is always half the percentage of meiosis in which crossing over takes place. Even if crossing over between 2 genes takes place in every meiosis, only 50% of the resulting gametes will be recombinants. Thus, the frequency of recombinant gametes is always half the frequency of crossing over, and the maximum proportion of recombinant gametes is 50%. Application. Let us apply what we have learned about linkage and recombination to a cross between tomato plants that differ homozygous recessive parent, which contain only the recessive alleles, resulting in mostly non-recombinant progeny and a few recombinant progeny. Figure 6. In this cross, we see that 55 of the test cross progeny have normal leaves and are tall, and 53 have model leaves and are dwarf. These plants are the non-recombinant progeny, containing the original combinations of traits that were present in the parents. Of the 123 progeny, 15 have new combinations of traits that were not seen in the parents. 8 are normal leaved and dwarf, and 7 are model leaved and tall. These plants are the recombinant progeny. The results of a cross such as the one illustrated in figure 6 reveal several things. A test cross for 2 independently assorting genes is expected to produce a 1 phenotypic ratio in the progeny. The progeny of this cross clearly do not exhibit such a ratio, so we might suspect that the genes are not assorting independently. When linked genes undergo crossing over, the result is mostly non-recombinant progeny and fewer recombinant progeny. This result is what we observe among the progeny of the test cross illustrated in figure 6, so we conclude that 2 genes show evidence of linkage with some crossing over. Calculation of recombination frequency. The percentage of recombinant progeny produced in a cross is called the recombination frequency, which is calculated as follows. Institute for Advanced Studies, Job 25. Recombinant _ number of recombinant progeny percent 100% frequency total number of progeny. In the test cross shown in figure 7, 15 progeny exhibit new combinations of traits, so the recombination frequency is IL 100% equals 2. And ET3 by 100% equals 12%. Thus, 12% of the progeny exhibit new combinations of traits resulting from crossing over. Tilde. Naddled. Feed. The normal brown puparium B. These loci are located close together on the second chromosome. Suppose we test cross a fly that is heterozygous at both loci with a fly that is homozygous recessive at both. Because these genes are linked, there are 2 possible arrangements on the chromosomes of the heterozygous fly. The dominant alleles for green thorax P** and brown puparium B might reside on the same chromosome, and the recessive alleles for purple thorax P and black puparium B might reside on the other homologous chromosome. This arrangement, in which wild type alleles are found on one chromosome and mutant alleles are found on the other chromosome, is referred to as coupling or the cis configuration. Alternatively, one chromosome might bear the alleles for green thorax P** and black puparium B, and the other chromosome would carry the alleles for purple thorax P and brown puparium B+. This arrangement, in which each chromosome contains one wild type and one mutant allele, is called the repulsion or transconfiguration. Whether the alleles in the heterozygous parent are in coupling or repulsion determines which phenotypes will be most common among the progeny of a test cross. When the alleles are in the coupling configuration, the most numerous progeny types are those with green thorax and brown puparium and those with purple thorax and black puparium. Figure 7a. But when the alleles of the heterozygous parent are in repulsion, the most numerous progeny types are those with green thorax and black puparium and those with purple thorax and brown puparium. Figure 7b. Notice that the genotypes of the parents in figure 7a and b are the same P** PPBX PPB, and that the dramatic difference in the phenotypic ratios of the progeny in the 2 crosses results entirely from the configuration, coupling or repulsion of the alleles in coupling configuration ID, all tells in repulsion. Chromosomes. It is essential to know the arrangement of the alleles on the chromosomes to accurately predict the outcome of crosses in which genes are linked. Relating independent assortment, linkage, and crossing over. We have now considered 3 situations concerning genes at different loci. First, the genes may be located on different chromosomes. In this case, they exhibit independent assortment and combine randomly when gametes are formed. An individual heterozygous at 2 loci AABB produces 4 types of gametes AB, AB, and AB in equal proportions, 2 types of non-recombinants and 2 types of recombinants. Second, the genes may be completely linked, meaning that they're on the same chromosome and lie so close together that crossing over between them is rare. In this case, the genes do not recombine. An individual heterozygous for 2 closely linked genes in the coupling configuration produces only the non-recombinant gametes containing alleles AB or AB. The alleles do not assort into new combinations such as A flat or AB. The third situation Incomplete linkage is intermediate between the two extremes of independent assortment and complete linkage. Here, the genes are physically linked on the same chromosome, which prevents independent assortment. However, occasional crossovers break up the linkage and allow them to recombine. With incomplete linkage, an individual heterozygous at two loci produces four types of gametes, two types of recombinants and two types of non-recombinants, but the non-recombinants are produced more frequently than the recombinants because crossing over does not take place in every meiosis. Linkage and crossing over are two opposing forces. Linkage binds alleles at different loci together, restricting their ability to associate freely, whereas crossing over breaks the linkage and allows alleles to assort into new combinations. Earlier, the term recombination was defined as the sorting of alleles into new combinations. We can now distinguish between two types of recombination that differ in the mechanism that generates these new combinations of alleles. Interchromosomal recombination is between genes on different chromosomes. It arises from independent assortment, the random segregation of chromosomes in anaphase meiosis. Interchromosomal recombination is between genes located on the same chromosome. It arises from crossing over, the exchange of genetic material in prophase meiosis. Both types of recombination produce new allele combinations in the gametes, so they cannot be distinguished by examining the types of gametes produced. Nevertheless, they can often be distinguished by the frequencies of types of gametes. Interchromosomal recombination produces 50% non-recombinant gametes and 50% recombinant gametes, whereas interchromosomal recombination frequently produces less than 50% recombinant gametes. However, when the genes are very far apart on the same chromosome, intrachromosomal recombination also produces 50% recombinant gametes. The two mechanisms are then genetically indistinguishable. The physical basis of recombination. Williamson's chromosome theory of inheritance, which stated that genes are physically located on chromosomes, was supported by many students and Edmund Wilson's discovery that sex was associated with a specific chromosome in insects and Calvin Bridges' demonstration that non-disjunction of X chromosomes was related to the inheritance of bicolor in Drosophila. Further evidence for the chromosome theory of heredity came in 1931, when Harriet Creighton and Barbara McClintock figure 8 obtained evidence that interchromosomal recombination was the result of physical exchange between chromosomes. Creighton and McClintock discovered a strain of corn that had an abnormal chromosome 9, containing a densely staining knob at one end and a small piece of another chromosome attached to the other end. This aberrant chromosome allowed them to visually distinguish the two members of a homologous pair. They studied the inheritance of two traits in corn determined by genes on chromosome 9. At one locus, a dominant allele C produced colored kernels, whereas a recessive allele C produced colorless kernels. At another, linked locus, a dominant allele WX produced starchy kernels, whereas a recessive allele WX produced waxy kernels. Creighton and McClintock obtained a plant that was heterozygous at both loci in repulsion, with the alleles for colored and waxy on the aberrant chromosome and the alleles for colorless and starchy on a normal chromosome. Knob extra piece. WX. Notice that, if crossing over entails physical exchange between the chromosomes, then the colorless, waxy progeny resulting from recombination should have a chromosome with an extra piece, but not a knob. Furthermore, some of the colored, starchy progeny should possess a knob but not the extra piece. This outcome is precisely what Creighton and McClintock observed, confirming the chromosomal theory of inheritance. Kirk Stern provided a similar demonstration by using chromosomal markers in Drosophila at about the same time, predicting the outcomes of crosses with linked genes. Knowing the arrangement of alleles on a chromosome allows us to predict the types of progeny that will result from a cross-entailing linked genes and to determine which of these types will be the most numerous. Determining the proportions of the types of offspring requires an additional piece of information, the recombination frequency. The recombination frequency provides us with information about how often the alleles in the gametes appear in new combinations and allows us to predict the proportions of offspring phenotypes that will result from a specific cross-entailing linked genes. In cucumbers, smooth fruit tea is recessive to warty fruit tea, and glossy fruit tea is recessive to dull fruit tea. Geneticists have determined that these two genes exhibit a recombination frequency of 16%. Suppose we cross a plant homozygous for warty and dull fruit with a plant homozygous for smooth and glossy fruit and then carry out a test cross by using the F1. What types and proportions of progeny will result from this test cross? Four types of gametes will be produced by the heterozygous parent, as shown in figure 9, two types of non-recombinant gametes T and T, and two types of recombinant gametes T and TD. The recombination frequency tells us that 16% of the gametes produced by the heterozygous parent will be recombinants. Because there are two types of recombinant gametes, each should arise with a frequency of 16%, 2 equals 8%. All the other gametes will be non-recombinants, so they should arise with a frequency of 100%, 16% equals 84%. Because there are two types of non-recombinant gametes, each should arise with a frequency of 84%, 2 equals 42%. The other parent in the test cross is homozygous and therefore produces only a single type of gamete TD with a probability of 1.00. The progeny of the cross result from a union of two gametes, producing four types of progeny. See figure 9. The expected proportion of each type can be determined by using the multiplication rule, multiplying together the probability of each uniting gamete. Test cross progeny with warty and dull fruit appear with a frequency of 0.42. The probability of inheriting a gamete with chromosome TD from the heterozygous parent by 1.00. The probability of inheriting a gamete with chromosome TD from the recessive parent equals 0.42. The proportions of the other types of F2 progeny can be calculated in a similar manner. See figure 9. This method can be used for predicting the outcome of any cross with linked genes for which the recombination frequency is known. Bits of the Tarnian the recombinase. Better than O gene equals 1. 1 S V parents and O predict the reals of crosses. The genes are obviously linked because there are clearly more non-recombinants than recombinants. In other crosses, the difference between independent assortment and linkage is not so obvious. For example, suppose we did a test cross for two pairs of genes, such as AABB x AABB, and observe the following numbers of progeny: 54 AABB, 56 AABB, 42 AABB, and 48 AABB. Is this outcome a 1:1:1 ratio? Not exactly, but it's pretty close. Perhaps these genes are sorting independently and chance produce a slight deviations between the observed numbers. Perhaps these genes are sorting independently and chance produce a slight deviations between the observed numbers and the expected 1:1:1 ratio. Alternatively, the genes might be linked, with considerable crossing over taking place between them, and so the number of non-recombinants is only slightly greater than the number of recombinants. How do we distinguish between the roles of chance and of linkage in producing deviations from the results expected with independent assortment? We encountered a similar problem in crosses in which genes were unlinked. The problem of distinguishing between deviations due to chance and those due to other factors. We addressed this problem with the goodness of fit chi-square test, which serves to evaluate the likelihood of the chance alone is responsible for deviations between observed and expected numbers. The chi-square test can also be used to test the goodness of fit between observed numbers of progeny and the numbers expected with independent assortment. Testing for independent assortment between two linked genes requires the calculation of a series of three chi-square tests. To illustrate this analysis, we will examine the data from a cross between German cockroaches, in which yellow body Y is recessive to brown body Y plus and curved wings CD or recessive to straight wings CD asterisk. A test cross YY CD X YY CD produced the following progeny: 63 Eotov 7 Yowie, 28 Tycho 32 Yodev, 200 total progeny. Brown body, straight wings, yellow body, curved wings, brown body, curved wings, yellow body, straight wings. Testing ratios at each locus to determine if the genes for body color and wing shape are sorting independently. We must examine each locus separately and determine whether the observed numbers differ from the expected. We will consider why this step is necessary at the end of this section. At the first locus for body color, the cross between heterozygote and homozygote YYXYY is expected to produce YY brown and YY yellow progeny, so we expect 100 of each. We observe 63 plus 28 equals 91 brown progeny and 77 plus 32 equals 109 yellow progeny. Applying the chi-square test to these observed and expected numbers, we obtain less than observed, expected, 91 to 100, 2 and 109 to 100, 2 be 100,100. 8181 100 plus 100 equals 0.81 plus 0.81 equals 1.622. The degrees of freedom associated with the chi-square test are n1, where n equals the number of expected classes. Here, there are 2 expected phenotypes, so the degree of freedom is 2 to 1 equals 1. Looking up our calculated chi-square value in table 3.4, we find that the probability associated with this chi-square value is between 0.30 and 0.20. Because the probability is above 0.05, our critical probability for rejecting the hypothesis that chance reduces the difference between observed and expected values, we conclude that there is no significant difference between the 1 ratio that we expect in the progeny of the test cross and the ratio that we observed. We next compare the observed and expected ratios for the second locus, which determines the type of wing. At this locus, a heterozygote and homozygote also were crossed CDT, CDX, CDED, and are expected to produce %CDCD straight wing progeny and %CDBCD curved wing progeny. We actually observe 63 plus 32 equals 95 straight wing progeny and 77 plus 28 equals 105 curved wing progeny, so the calculated chi-square value is 95 to 100, 2 and 105 to 100 degree 100,100. 25 4 plus 25 equals 5910 plus 100 equals 0.20 plus 0.2. 2. 3 3 LI equals O equals. The degree of freedom associated with this chi-square value also is 2 1 equals 1, and the associated probability is between 0.5 and 0.3. We again assume that there is no significant difference between what we observed and what we expected at this locus in the test cross. Testing ratios for independent assortment. We are now ready to test for the independent assortment of genes at the 2 loci. If the genes are assorting independently, we can use the multiplication rule to obtain the probabilities and numbers of progeny inheriting different combinations of phenotypes. Expected. Genetic phenotype expected observed. TBPDS types tions numbers. V at O B Brown. Yo YY equals 5063. Straight. Here, we have 4 expected classes of phenotypes, so the degrees of freedom equal 4 to 1 equals 3 and the associated probability is considerably less than 0.001. This very small probability indicates that the phenotypes are not in the proportions that we would expect if independent assortment were taking place. Our conclusion, then, is that these genes are not assorting independently and must be linked. In summary, testing for linkage between 2 genes requires a series of chi-square tests. A chi-square test for the segregation of alleles at each individual locus, followed by a test for independent assortment between alleles at the different loci. The chi-square test for segregation at individual loci should always be carried out before testing for independent assortment, because the probabilities expected with independent assortment are based on the probabilities expected at a separate loci. Suppose that the genes in the cockroach example were assorting independently and that some of the cockroaches with curved wings died in embryonic development. The observed proportion with curved wings was then 1/3 instead of %.1 in this case. The proportion of offspring with yellow body and curved wings expected under independent assortment should be 1/3 by 1/2 equals 1/6 instead of %. Without the initial chi-square test for segregation at the curved wing locus, we would have no way of knowing that what we expected with independent assortment was 1/6 instead of %. If we carried out only the final test for independent assortment and assumed an expected 1 ratio, we would obtain a high chi-square value. We might conclude, erroneously, that the genes were linked. If a significant chi-square, one that has a probability less than 0.05, is obtained in either of the first 2 tests for segregation, then the final chi-square for independent assortment should not be carried out, because the true expected values are unknown. Gene mapping with recombination frequencies. Morgan and his students developed the idea that physical distances between genes on a chromosome are related to the rates of recombination. They hypothesized that crossover events occur more or less at random up and down the chromosome, and that 2 genes that lie far apart are more likely to undergo a crossover than are 2 genes that lie close together. They proposed that recombination frequencies could provide a convenient way to determine the order of genes along a chromosome and would give estimates of the relative distances between the genes. Chromosome maps calculated by using recombination frequencies are called genetic maps. In contrast, chromosome maps based on physical distances along the chromosome, often expressed in terms of numbers of base pairs, are called physical maps. Distances on genetic maps are measured in map units. Abbreviated M. U. 1 map unit equals 1% recombination. Map units are also called centimorgans. CM in honor of Thomas Hunt Morgan. 1 morgan equals 100 meters. U. Genetic distances measured with recombination rates are approximately additive. If the distance from gene A to gene B is 5 meters, U. The distance from gene B to gene C 10 meters, U. And the by doing a series of crosses between pairs of genes, we can construct genetic maps showing the linkage arrangements of a number of genes. 2 points should be emphasized about constructing chromosome maps from recombination frequencies. First, recall that the recombination frequency between 2 genes cannot exceed 50% and that 50% is also the rate of recombination for genes located on different chromosomes. Consequently, one cannot distinguish between genes on different chromosomes and genes located far apart on the same chromosome. If genes exhibit 50% recombination, the most that can be said about them is that they belong to different groups of linked genes. Different linkage groups either on different chromosomes or far apart on the same chromosome. OIB double crossover. A single crossover. We'll switch the underscore dot but a second crossover YRLL. Remember the f-text of the first, mass storing the original. A second point is that a test cross for 2 genes that are relatively far apart on the same chromosome tends to underestimate the true recombination frequency, because the cross does not reveal double crossovers that might take place between the 2 genes. Figure 10. A double crossover arises when 2 separate crossover events take place between the same 2 loci. Whereas a single crossover switches the alleles on the homologous chromosomes, producing combinations of alleles that were not present on the original parental chromosomes. A second crossover between the same 2 genes reverses the effects of the first, thus restoring the original parental combination of alleles. Double crossovers produce only non-recombinant gametes, and we cannot distinguish between the progeny produced by double crossovers and the progeny produced when there is no crossing over. However, as we shall see in the next section, it is possible to detect double crossovers if we examine a third gene that lies between the 2 crossovers. Because double crossovers between 2 genes go undetected, recombination frequencies will be underestimated whenever double crossovers take place. Double crossovers are more frequent between genes that are far apart. Therefore, genetic maps based on short distances are always more accurate than those based on longer distances. Constructing a genetic map with 2-point test crosses. Genetic maps can be constructed by conducting a series of test crosses between pairs of genes and examining the recombination. Genetic maps can be constructed by conducting a series of test crosses between pairs of genes and examining the recombination frequencies between them. A test cross between 2 genes is called a 2-point test cross or a 2-point cross for short. Suppose that we carried out a series of 2-point crosses for 4 genes, A, B, cent, and D, and obtained the following recombination frequencies. Gene loci and test cross recombinant frequency %. A and D, B 50, A and D, C 50 on D 50 band C 20 band 10 can 28. We can begin constructing a genetic map for these genes by considering the recombination frequencies for each pair of genes. The recombination frequency between N, B is 50%, which is the recombination frequency expected with independent assortment. Genes N, B may therefore either be on different chromosomes or be very far apart on the same chromosome, so we will place them in different linkage groups with the understanding that they may or may not be on the same chromosome. Linkage group 1. Linkage group 2. The recombination frequency between N, C is 50%, indicating that they, too, are in different linkage groups. The recombination frequency between B and C is 20%, so these genes are linked and separated by 20 map units. Linkage group 1. Linkage group 2. B, C. L. 20 ma. The recombination frequency between N, D is 50%, indicating that these genes belong to different linkage groups, whereas genes B and D are linked, with a recombination frequency of 10%. To decide whether gene D is 10 map units to the left or right of gene B, we must consult the C to D distance. If gene D is 10 map units to the left of gene B, then the distance between D and C should be 20 meters, U. plus 10 meters, u, equals 30 meters, u. This distance will be only approximate because any double crossovers between the two genes will be missed and the recombination frequency will be underestimated. If, on the other hand, gene D lies to the right of gene B, then the distance between gene D and C will be much shorter. Approximately 20 meters, u, 10 meters, u, equals 10 meters, u. By examining the recombination frequency between Z and D, we can distinguish between these two possibilities. The recombination frequency between C and D is 28%, so gene D must lie to the left of gene B. Notice that the sum of the recombination between D and B 10% and between B and Z 20% is greater than the recombination between D and Z 28%. This is what was meant by saying that recombination rates, i.e., map units, are approximately additive. This discrepancy arises because double crossovers between the two outer genes go undetected, causing an underestimation of the true recombination frequency. The genetic map of these genes is now complete. Linkage group 1. Linkage group 2. DBC. 10 meters, u, 20 meters, u, 30 meters, u. Linkage and recombination between three genes. Genetic maps can be constructed from a series of test crosses for pairs of genes, but this approach is not particularly efficient because numerous two-point crosses must be carried out to establish the order of the genes and because double crossovers are missed. A more efficient mapping technique is a test cross for three genes, a three-point test cross, or three-point cross. With a three-point cross, the order of the three genes can be established in a single set of progeny and some double crossovers can usually be detected, providing more accurate map distances. Central YINNNC. Consider what happens when crossing over takes place among three hypothetical linked genes. Figure 11 illustrates a pair of homologous chromosomes from an individual that is heterozygous at 3 loci AABBCC. Notice that the genes are in the coupling configuration, that is, all the dominant alleles are on one chromosome A_BC and all the recessive alleles are on the other chromosome __B. C. Three types of crossover events can take place between these three genes. Two types of single crossovers, see figure 11A and B, and a double crossover, see figure 11C. In each type of crossover, two of the resulting chromosomes are recombinants and two are non-recombinants. Notice that in the recombinant chromosomes resulting from the double crossover, the outer two alleles are the same as in the non-recombinants, but the middle allele is different. This result provides us with an important clue about the order of the genes. In progeny that result from a double crossover, only the middle allele should differ from the alleles present in the non-recombinant progeny. Gene mapping with the three-point test cross. To examine gene mapping with a three-point test cross, we will consider three recessive mutations in the fruit fly Drosophila melanogaster. In this species, scarlet-eyed streak or recessive to red-eyed streak ebony body color E is recessive to gray body color E, and spineless SS, that is, the presence of small bristles, is recessive to normal bristles SS asterisk. All three mutations are linked and located on the third chromosome. We will refer to these three loci as Saint, E, and SS, but keep in mind that either recessive alleles streak, E, and SS, or the dominant alleles streak plus, E plus, and SS asterisk may be present at each locus. So, when we say that there are 10 meters, U, between streak and SS, we mean that there are 10 meters, U, between the loci at which these mutations occur. We could just as easily say that there are 10 meters, U, between streak and SS asterisk. To map these genes, we need to determine their order on the chromosome and the genetic distances between them. First, we must set up a three-point test cross, a cross between a fly heterozygous at all three loci and a fly homozygous for recessive alleles at all three loci. To produce flies heterozygous for all three loci, we might cross a stock of flies that are homozygous for normal alleles at all three loci with flies that are homozygous for recessive alleles at all three loci. F. The order of the genes has been arbitrarily assigned because at this point we do not know which is the middle gene. Additionally, the alleles in these heterozygotes are in coupling configuration because all the wild-type dominant alleles were inherited from one parent and all the recessive mutations from the other parent, although the test cross can also be done with genes in repulsion. In the three-point test cross, we cross the F1 heterozygotes with flies that are homozygous for all three recessive mutations. In many organisms, it makes no difference whether the heterozygous parent in the test cross is male or female, provided that the genes are autosomal, but in Drosophila, no crossing over takes place in males. Because crossing over in the heterozygous parent is essential for determining recombination frequencies, the heterozygous flies in our test cross must be female. So we make female F1 flies that are heterozygous for all three traits with male flies that are homozygous for all the recessive traits. Sidet streak streak ES, female X, malice East SS streak ESS. The progeny produced from this cross are listed in figure 12. For each locus, two classes of progeny are produced, progeny that are heterozygous, displaying the dominant trait, and progeny that are homozygous, displaying the recessive trait. With two classes of progeny possible for each of the three loci, there will be 23 equals 8 classes of phenotypes possible in the progeny. In this example, all 8 phenotypic classes are present, but in some three-point crosses, one or more of the phenotypes may be missing if the number of progeny is limited. Nevertheless, the absence of a particular class can provide important information about which combination of traits is least frequent and ultimately the order of the genes, as we will see. To map the genes, we need information about where and how often crossing over has occurred. In the homozygous recessive parent, the two alleles at each locus are the same. And so crossing over will have no effect on the types of gametes produced. With or without crossing over, all gametes from this parent have a chromosome with three recessive alleles streak_ESS. In contrast, the heterozygous parent has different alleles on its two chromosomes, so crossing over can be detected. The information that we need for mapping, therefore, comes entirely from the gametes produced by the heterozygous parent. Because chromosomes contributed by the homozygous parent carry only recessive alleles, whatever alleles are present on the chromosome contributed by the heterozygous parent will be expressed in the progeny. As a shortcut, we usually do not write out the complete genotypes of the test cross progeny, listing instead only the alleles expressed in the phenotype as shown in figure 12, which are the alleles inherited from the heterozygous parent. Forward right stroller, Ebori. TN, Sophilus OB, BAAL, SSS. Determining the gene order, the first task in mapping the genes is to determine the order on the chromosome. In figure 12, we arbitrarily listed the loci in the order streak, E, SS. But we had no way of knowing which of the three loci was between the other two. We can now identify the middle locus by examining the double crossover progeny. First, determine which progeny are the non-recombinants. They will be the two most numerous classes of progeny. Even if crossing over takes place in every meiosis, the non-recombinants will comprise at least 50% of the progeny. Among the progeny of the test cross in figure 13, the most numerous are those with all three dominant traits, streak_ESS asterisk, and those with all three recessive traits, streak_ESS. Next, identify the double crossover progeny. These should always be the two least numerous phenotypes, because the probability of a double crossover is always less than the probability of a single crossover. The least common progeny among those listed in figure 12 are progeny with red eyes, gray body, and spineless bristles, streak_ESS, and progeny with scarlet eyes, ebony body, and normal bristles, streak ESS asterisk, so they are the double crossover progeny. Three orders of genes are possible. The eye color locus could be in the middle, E streak SS. The body color locus could be in the middle, streak_ESS, or the bristle locus could be in the middle, streak_SSE. To determine which gene is in the middle, we can draw the chromosomes of the heterozygous parent with all three possible gene orders and then see if the double crossover produces the combination of genes observed in the double crossover progeny. The three possible gene orders and the types of progeny produced by their double crossovers are original chromosomes after crossing over at STT, SST, STT, SST, streak STSE, ESTS. STT at SST, STT at SST, STTV streak. The only gene order that produces chromosomes with alleles for the traits observed in the double crossovers, streak E asterisk. With a little practice, it's possible to quickly determine which locus is in the middle without writing out all the gene orders. The phenotypes of the progeny are expressions of the alleles inherited from the heterozygous parent. Recall that when we look at the results of double crossovers, see figure 12, only the alleles of the middle locus differ from the non-recombinants. If we compare the non-recombinant progeny with double crossover progeny, they should differ only in alleles of the middle locus. Let's compare the alleles in the double crossover progeny streak E asterisk_SS with those in the non-recombinant progeny streak E plus SS asterisk. We see that both have an allele for red-eyed streak and both have an allele for gray body E, but the non-recombinants have an allele for normal bristles SS asterisk, whereas the double crossovers have an allele for spineless bristles SS. Because The bristle locus is the only one that differs. It must lie in the middle. We would obtain the same results if we compared the other class of double crossover progeny, straight DSS asterisk, with other non-recombinant progeny, straight DSS. Again, the only trait that differs is the one for bristles. Don't forget that the non-recombinants and the double crossovers should differ only at one locus. If they differ in two loci, the wrong classes of progeny are being compared. Institute for Advanced Studies, Job 33. Determining the locations of crossovers when we know the correct order of the loci on the chromosome, we should rewrite the phenotypes of the test cross progeny in figure 13 with the loci in the correct order so that we can determine where crossovers have taken place. Figure 13. Among the 8 classes of progeny, we have already identified 2 classes as non-recombinants, straight SS asterisk E and SSE, and 2 classes as double crossovers, straight SSE and SS asterisk E. The other 4 classes include progeny that resulted from a chromosome that underwent a single crossover. 2. Underwent single crossovers between straight and SS, and 2. Underwent single crossovers between SS and E. To determine where the crossovers took place in these progeny, compare the alleles found in the single crossover progeny with those found in the non-recombinants, just as we did for the double crossovers. Some of the alleles in the single crossover progeny are derived from one of the original non-recombinant chromosomes of the heterozygous parent, but at some place there is a switch due to crossing over, and the remaining alleles are derived from the homologous non-recombinant chromosome. The position of the switch indicates where the crossover event took place. For example, consider progeny with chromosome straight SSE. The first allele straight came from the non-recombinant chromosome straight SS asterisk E, and the other 2 alleles SS and E must have come from the other non-recombinant chromosome straight underscore. This same method can be used to determine the location of crossing over in the other 2 types of single crossover progeny. Crossing between SS and E's produces straight underscore SS asterisk East and saint underscore SSE chromosomes. 6 straight at STTTSST at STTTSS. Recombination frequency is calculated by adding up all of the recombinant progeny, dividing this number by the total number of progeny from the cross, and multiplying the number obtained by 100%. To determine the map distances accurately, we must include all crossovers, both single and double, that take place between 2 genes. Recombinant progeny that possess a chromosome that underwent crossing over between the I color locus straight and the bristle locus SS include the single crossovers straight SS East, SST at plus, and the 2 double crossovers straight SS Aarons, SSE, see figure 13. There are a total of 755 progeny, so the recombination frequency between SS and saint is saint SS recombination frequency equals. Finally, calculate the genetic distance between the outer 2 loci, straight and E. Add up all the progeny with crossovers between the 2 loci. These progeny include those with a single crossover between straight and SS, those with a single crossover between SS and E, and the double crossovers straight SS Aarons, SSE. Because the double crossovers have 2 crossovers between straight and E, we must add the double crossovers twice to determine the recombination frequency between these 2 loci. Notice that the distances between straight and SS 14.6 meters, U, and between SS and E 12.2 meters, U. Add up to the distance between straight and E 26.8 meters, U. We can now use the map distances to draw a map of the 3 genes on the chromosome. 26.8. Interference and coefficient of coincidence map distances give us information not only about the physical distances that separate genes, but also about the proportions of recombinant and non-recombinant gametes that will be produced in a cross. For example, knowing that genes straight and SS on the 3rd chromosome of D. melanogaster are separated by a distance of 14.6 meters, U, tells us that 14.6% of the gametes produced by a fly heterozygous of these 2 loci will be recombinants. Similarly, 12.2% of the gametes from a fly heterozygous for SS and E will be recombinants. Theoretically, we should be able to calculate the proportion of double recombinant gametes by using the multiplication rule of probability, which states that the probability of 2 independent events occurring together is the multiplication of their independent probabilities. Applying this principle, we should find that the proportion probability of gametes with double crossovers between straight and E is equal to the probability of recombination between straight and SS, multiplied by the probability of recombination between SS and E, or 0.146 by 0.122 equals 0.0178. Multiplying this probability by the total number of progeny gives us the expected number of double crossover progeny from the cross. 0.0178 x 755 equals 13.4. Only 8 double crossovers, considerably fewer than the 13 expected, were observed in the progeny of the cross. This phenomenon is common in eukaryotic organisms. The calculation assumes that each crossover event is independent and that the occurrence of one crossover does not influence the occurrence of another. But crossovers are frequently not independent events. The occurrence of one tends to inhibit additional crossovers in the same region of the chromosome, and so double crossovers are less frequent than expected. The degree to which one crossover interferes with additional crossovers in the same region is termed the interference. To calculate the interference, we first determine the together is the multiplication of their independent probabilities. Applying this principle, we should find that the proportion probability of gametes with double crossovers between straight and E is equal to the probability of recombination between straight and SS, multiplied by the probability of recombination between SS and E, or 0.146 0.122 equals 0.0178. Multiplying this probability by the total number of progeny gives us the expected number of double crossover progeny from the cross. 0.0178 x 755 equals 13.4. Only 8 double crossovers, considerably fewer than the 13 expected, were observed in the progeny of the cross. See figure 12. This phenomenon is common in eukaryotic organisms. The calculation assumes that each crossover event is independent and that the occurrence of one crossover does not influence the occurrence of another. But crossovers are frequently not independent events. The occurrence of one tends to inhibit additional crossovers in the same region of the chromosome, and so double crossovers are less frequent than expected. The degree to which one crossover interferes with additional crossovers in the same region is termed the interference. To calculate the interference, we first determine the coefficient of coincidence equals number of observed double crossovers, number of expected double crossovers. For the loci that we mapped on the 3rd chromosome of D. melanogaster, see figure 13, we find that coefficient of coincidence equals 5 plus 380.146 by 0.122 x 755 13.4. Which indicates that we are actually observing only 60% of the double crossovers that we expected on the basis of the single crossover frequencies. The interference is calculated as interference 1 equals coefficient of coincidence. The interference for our 3-point cross is interference equals 1 minus 0.6 equals 0.4. This value of interference tells us that 40% of the double crossover progeny expected will not be observed because of interference. When interference is complete and no double crossover progeny are observed, the coefficient of coincidence is 0 and the interference is 1. Sometimes more double crossover progeny appear than expected, which happens when a crossover increases the probability of another crossover occurring nearby. In this case, the coefficient of coincidence is greater than 1 and the interference will be negative. Institute for Advanced Studies, Job 35. Gene mapping in humans. Efforts in mapping the human genome are hampered by the inability to perform desired processes in a small number of progeny in most human families. Geneticists are restricted to analyses of pedigrees, which are often incomplete and provide limited information. Nevertheless, techniques have been developed that use pedigree data to analyze linkage, and a large number of human traits have been successfully mapped with the use of these methods. Because the number of progeny from any one mating is usually small, data from several families and pedigrees are usually combined to test for independent assortment. The methods used in these types of analysis are beyond the scope of this book, but an example will illustrate how linkage can be detected from pedigree data. One of the first documented demonstrations of linkage in humans was between the locus for Nail-Patella syndrome and the locus that determines the ABO blood types. Nail-Patella syndrome is an autosomal dominant disorder characterized by abnormal fingernails and absent or rudimentary kneecaps. The ABO blood types are determined by an autosomal locus with multiple alleles. Linkage between the genes encoding these traits was established in families in which both traits segregate. Part of one such family is illustrated in figure 14. Nail-Patella syndrome is relatively rare, so we can assume that people having this trait are heterozygous N and unaffected people are homozygous NN. The ABO genotypes, there is no recombination among the offspring of these parents, generation 2, but there are 2 instances of recombination among the persons in generation IIL. Individuals 2 1 and 2 2 have the following genotypes. Their child on 1 and 2 has blood type A and does not have Nail-Patella syndrome, so he must have genotype and must have inherited both the I and the N alleles from his father. These alleles are on different chromosomes in the father, so crossing over must have taken place. Crossing over also must have taken place to produce child 33. In the pedigree